now let's deal with a more complex circuit. So let's deal with an RLC in series. So I have a resistor, an inductor, and a capacitor in series. Now, so the big question is, what is common to all things in series? And that would be the current. So actually, it's the instantaneous as well. So current is the same for all components. So because that is the case, when we do our phasor diagram here, we will draw the current first. So the thing that is in common is the thing probably easiest to do. We'll eventually do a circuit where it's not necessarily obvious, which is the one we're doing. So this is our current right here. Label it with a capital I. It is the current. I could also label it as I sub R, I sub L, I sub C, and I sub power supply. All those are viable, but the current is the same for all of them. So if you ever have a problem which asks you to draw a phasor diagram and have the current for each component, something like that would be drawn. So now we're going to do voltages. Now I know for the current and the voltage across the resistor are in phase. So I'm going to draw the voltage for the resistor. And then I want to do, and now the other two, that is capacitor there. For the inductor, voltage leads the current. And so the inductor, it leads by 90 degrees, so that's a right angle right there. This is the voltage for the inductor. So, and then for a capacitor, don't forget, Eli is an Iceman. So for the capacitor, current comes first. So again, these phasors are traveling around counterclockwise. So V sub C is traveling down in that direction. And I want to figure out the EMF. And so, unfortunately, I don't have a bigger screen here, so I'm going to have to erase that. Presumably, you paused this video and have written the stuff down. But we need to somehow add the 3 voltages in order to get the voltage across the power supply. Because remember, Kirchhoff's rule applies here. Whatever voltage gain we have across here, we're going to lose that much voltage going across there. So the sum of the 3 voltages across the components should equal the voltage going across the power supply. Do green axes, because why not? And then our current, I forget what color I used, current I. And then our voltages, I used black. So I have V sub R, V sub C, and V sub L. Now I don't know which is bigger, VL or VC. So I'm just going to make an assumption. I'm going to assume VL is greater than VC. And I don't know for sure, but it doesn't really matter because we'll end up, well, hopefully you'll see why it doesn't really matter which one we assume. So if VL is bigger than VC, then if I add them together, I add them like vectors. You know, think head to tail here. The sum is going to be a phasor in this direction with this magnitude of VL minus VC. VR is still in that direction right there. And then my current is pointing in that direction. If we assumed VC was bigger than VL, it would have been going in that direction. We'll do orange. So if this would be VC minus VL, however, we are not doing that, and so this is what we're left with. All right, about to erase this screen. And erase. Set up my axes again. And we have our current going in this direction. We have V sub R that way, and then we have our VL minus VC. This is a right angle here. Now, the EMF should be the sum of these two vectors here. that should be the EMF. And since we're dealing with a right angle here, this is basically a rectangle, I know that Pythagorean theorem holds true here. So VR squared plus VL minus VC squared equals the EMF squared. So since VR, so now you see if we'd chosen VC being bigger than VL, then this term right here would have just been the opposite, but squaring it is just going to make it positive no matter what. So now we're trying to find the impedance here. So we need to get an equation that's basically in the form of E equals I times Z. And so we're basically going to solve for the EMF in terms of the current. So I'm going to need to erase this. I have to hopefully remember that equation right there. EMF squared equals VR squared plus VL minus VC squared. Now we use the Ohm's law variations. So I know that VR is equal to I times R squared plus VL I know is I times X sub L. VC is I times X sub C. That squared. I can factor I squared out, so this is I squared times R squared plus XL minus X sub C squared. So this becomes I squared times R squared plus omega L minus 1 over omega C squared. And so now on to the next page. Epsilon squared is equal to I squared squared times R squared plus omega L minus 1 over omega C squared. And if I take the square root of both sides, I get epsilon is equal to I times the square root of R squared plus omega L minus 1 over omega C squared. This is now in the form that I want. Epsilon is equal to IZ, or Z, as it's rightfully said. And so that right there, and let's highlight in a slightly different color there, just to emphasize, those parallel right there. And so for this particular formula here, the impedance for the RLC series circuit is the square root of R squared plus omega L minus 1 over omega C squared. So if I told you the angular frequency and the capacitance and the inductance and the resistance, you should be able to find it. And remember well, actually you haven't done it yet. So for stuff coming out of our sockets, this generally runs around 370 radians per second is value for omega, just to give you some sort of sense there. All right, so that's the RLC series circuit.